Hi, my name is Dana Golden. We're going to continue on with our electricity markets lecture with a look at generation. I'm going to start off by looking at the types of power generation and really think about how these types of power generation feed into the costs. Because the cost structure and the ability to provide electricity whenever you want are really what determine how you should think about generation economically. So it's really interesting in energy market economics how cost and technical factors feed into economic factors, and that's what I want to share with you. So types of generation: fossil fuels. Coal has high carbon emissions, but has been historically dominant. Natural gas has lower emissions and is flexible, is widely used in peaking plants, which are the plants that come online in the middle of the day, and oil is not that much used for electricity generation. It's typically used for backup or niche applications. For example, if you go to our computer science school here at Stony Brook, if you go to the new computer science building, you look out and you see a diesel generator. And that's because at that scale of needing a backup for our data resources, it makes sense to have a diesel generator for electricity. It doesn't make sense basically anywhere else because it's only makes sense for like a very small use or for backup power. And then, of course, we have renewable energy, which I think all of us are very excited about based on the fact that you took this class. I hope you're excited about it. And that includes solar, which harnesses sunlight. It's intermittent. Intermittency is a very important thing in this class, and it's going to be very important for the rest of this class for you to think about intermittency. And basically what intermittency means is that a generator can't be run whenever you want it to. It only runs certain times of the day, sometimes without you being able to control it, and it requires a storage or backup to take care of electricity when you're not using it. Wind utilizes wind turbines, so this, instead of using steam to spin the turbines, it uses the wind to create that mechanical energy to spin the turbine. It requires grid flexibility. Hydropower is reliable and long-lasting, but dependent upon location. And then biomass uses organic materials. I say here considered carbon neutral. That's not really true anymore. It used to be seen as a very clean fuel. Recently, people have decided, actually, because of some of the emissions it produces, we shouldn't be using biomass. We shouldn't treat it the same as solar. And then we have nuclear power, which is kind of an oddball from a power standpoint because it's not renewable, it's not fossil. It's carbon clean. They're very limited emissions. There's some emissions, but they're not coming from nuclear power. You could also count the emissions from the waste, but we're pretty good at storing that. Provides large-scale baseload power. When I say baseload, I mean this is the power you can rely on. There's no intermittency with no direct emissions, but they're high upfront costs. Long construction times, just hard to deal with it. So as the fuel mix changed over time, how has the electricity market evolved? In the early era, this was a market dominated largely by coal due to coal's abundance and how easy it was to transport. Then in the mid-20th century, we saw the rise of oil and natural gas with advancements in extraction and pipelines. Then nuclear power emerged as a baseload source of energy. And in recent decades, there's been a shift towards renewables driven by climate policies and falling costs. The cost of a solar panel, I have a graph I frequently look at on the cost of a solar panel over time. It's gone down dramatically. It's just fallen like a rock. I'd use that in my research. It's just pretty incredible how renewables used to be a more expensive resource and now they're cheaper. Natural gas also replaced coal in many regions, especially in the United States, due to the lower emissions, because coal became untenable to the emissions, and also cost effectiveness with the combined cycle natural gas and the fracking revolution, making natural gas really a competitive fuel which it didn't used to be. It used to be too inefficient, and it used to be too expensive to use. It still is too expensive in some places, like Europe, and is moving back towards coal. I don't think they want to. India and China are using a lot of coal. I think they want to, though. But I think China, at least, would like to pretend like it would like to move away from coal, even if it acknowledges that the cost savings are pretty significant. So renewables now represent the largest share of new capacity additions. There's a growing focus today on energy storage and grid modernization. So adding a more modernized grid that can go long distances for transmission and adding storage resources is really the current trends in working in the fuel mix. So here is the, I used to have a professor, his name was Doran Lubinsky. I hope I'm saying that right if you watch this. He was my multivariable calculus professor, and he would, multiple times in the semester, he would always, whenever we did a transformation to polar coordinates, he would always say, "Let's go polar." So yeah, let's go solar. Yeah, so we historically most of the energy was coming from wood, and then we had the first industrial revolution, and things started coming from coal, and then coal was replaced by petroleum. Petroleum is still a major part of energy consumption. Remember, this is energy and not electricity. And now you're seeing the rise of renewables over time. Natural gas has gone up, but it will start soon to go down. So let's talk about some of the things you'll think about if you're working in these markets, and like how you think about these resources. So first thing I want to talk about is the capacity factor. And this measures how efficiently a power plant operates over a specific period compared to its maximum possible output. So this is the actual energy generated over the maximum possible energy times 100%. So this is really how efficient the generator is. So this is the total electricity produced by the plant during the day, typically measured in megawatt hours, divided by the rated capacity provided by the EIA, usually different in summer and winter because of heat requirements and how they affect different types of plants. It's expressed as a percentage and provides insight into utilization. So nuclear has the highest capacity factor by far. Basically, the only time you have a nuclear plant offline is when you're doing maintenance. So I have some friends who used to work at nuclear power plants. They would do a 2-week maintenance once a year, where they had to go into the plant all the time and do the maintenance. The number I always hear is 92%, but it varies. It's somewhere between 80 and 95% for capacity factor for nuclear. Coal is about 40 to 7%. This bit depends a lot on where your coal fire plant is. It's gone down a lot over the years because it's just not cost competitive anymore. Natural gas is like also in this range, like 50 to 70%, I think. Wind is mainly 20 to 50%. This is really onshore wind. Offshore wind gets a little bit above this, which is why there's a lot of research being done there. I actually just finished up a paper with some engineers from our department and with my advisor, focusing on some techno-economic analysis of offshore wind. And the capacity factor is a lot higher, but there's a lot of unique challenges to offshore wind. And then solar, 10 to 30%. Thin film is one technology we'll talk about. Photovoltaics is the main technology. Photovoltaics is about 10 to 30%, but it really depends on where you're putting on the solar farm. In the Southeast, it's really productive. Texas is really productive. In the New England, there are tons of solar farms, tons of very small solar farms. They have remarkably low capacity factors. Factors affecting capacity: weather, which impacts renewables like wind and solar; maintenance, downtime reduces capacity factors; and demand. If demand is low, plants will not operate at full capacity. So how do we calculate capacity factor? We have a wind farm that's capacity of 100 megawatts and generates 175,200 megawatt hours of electricity in a year. Calculates capacity factor. So first off, you calculate the maximum possible energy output. Maximum energy equals capacity times hours in a year. 100 megawatts times 1,760 hours equals 876,000 megawatts hours. And then you divide that actual energy generated, 175,200, by the maximum possible energy, multiplied by 100%. You get the wind farm operates at 20% of its full capacity over the year. Now we'll talk about the cost of electricity, and capacity factors are a direct feed in to both the cost of electricity and the levelized cost of electricity. So the cost of electricity reflects the price required to produce and deliver electricity to consumers, covering all production, transmission, distribution expenses. This includes capital costs, the investment in power plants, infrastructure, and equipment. Operation and maintenance costs, regular expenses for running and maintaining power plants. This is usually someone's salary. This is usually the engineers, but also probably the HR person, maybe the CEO. Fuel costs. For fossil fuel plants, fuel expenses dominate. Renewable plants don't have any fuel costs. They have low marginal costs. And for nuclear plants, fuel costs are so dominated by fixed costs that the cost of uranium is essentially irrelevant to running a nuclear plant. And not fully irrelevant, but pretty irrelevant. And then transmission distribution costs, the cost of transport electricity from generation sites to customers. Just a reminder, you're going to lose some of the electricity to thermal factors, to thermal heat. And then this allows you, the cost of electricity allows you to determine competitiveness of different energy sources, and it impacts how electricity is priced. So let's calculate the cost of electricity. A power plant generates 1,000 megawatt hours of electricity in a year. The total cost includes capital costs, operation and maintenance costs, fuel costs. So we add these together, and then we calculate the cost per megawatt, total cost divided by total generation, 650 per megawatt. And then now, the levelized cost of energy is the average cost of electricity over the plant's lifetime, considering all costs and generation. So this was, the cost for a particular year, and it's not levelized by taking into account all costs and generation over a lifetime. So key factors here, again, capital costs, how expensive it is to build the plant, materials and labor. This is higher for renewable sources. Renewable sources have a high fixed cost, low variable cost, high upfront investment. Then operation and maintenance costs, the regular expenses for operation upkeep, and this varies by technology. Pretty low for solar, pretty high for nuclear. You need people there to run the plant. And then fuel cost is relevant for fossil fuel plants and negligible for resources or for renewables. Maybe biofuel has a little bit of fuel cost. Solar and wind really don't. And then higher utilization reduces LCOE by spreading fixed costs over more output. So a higher capacity factor reduces LCOE and makes the system more economical. And discount rate reflects the time value of money, impacting long-term estimates of costs. We talked about this a lot in cost-benefit analysis. So here's the levelized cost of electricity, also potentially levelized cost of energy, depending on who you're hearing it from. So this is equal to the sum from T equals 1 to T, investment costs, operation maintenance costs, fixed costs, discounted by each period, depending on the period in which they're incurred, over the energy costs, discounted by the interest rate over the period they're incurred. So T is the project lifetime, so you're counting this every time in the project, even after you close down the plant. So this LCOE generally starts before and after you close down the plant, because you might have costs in decommissioning, and you might have revenues in decommissioning because you might have a scrap value, and you might also have a costs in just building it. You will have costs in just building it. And the investment costs in UT, fuel costs in UT. This was not fixed costs. I shouldn't have said fixed costs. This is fuel costs. And then electricity generated in UT and discount rate. So the numerator is the present total value of total cost over the project lifetime, and the denominator is the present value of total electricity generation. And the LCOE is given in cost per megawatt hours. This allows you to compare the cost of electricity across generation types. Here's an example calculation. A solar plant has capital cost of $1 million, operation and maintenance cost of $20,000, no fuel costs because it's solar, annual generation of 5,000 megawatt hours. This can go on bottom after we discount it. project lifetime of 20 years, and a discount rate of 5%. So let's start by calculating the present value of the cost of electricity. 1 million over 1.05, that's the upfront cost you have to pay. This ratio is 0 because we're not discounting it at all. We pay it today. And then for 20 years, we have to pay these operating and maintenance costs, which are much smaller, but we had the high upfront cost. And that ends up being equal to this number. And then the present value of generation is equal to 5,000, how much we expect it to generate each year. Remember, this is based on the capacity factor times the max capacity. Discounted, you get this number, and then you divide the two numbers. You divide the cost by the generation, and then you get this number. The LCOE for the solar plant is approximately 20.97, which means that if electricity is more expensive than that, then the solar plant is a good investment. If electricity is less expensive than that, solar plant is a bad investment. So you can pretty directly compare the LCOE to the price of electricity, the expected price of electricity, and determine if you should be making the investment. So also something people do pretty often is they perform sensitivity analyses on LCOE to understand how changing key variables affect the levelized cost of electricity, helping stakeholders make informed decisions. And so they look at the change in capital costs, particularly, is it possible that we impact over budgeted or under budgeted expenses? You want to know like how much you're affected by a change in your assumption about capital. Then operation and maintenance cost. What if maintenance costs more? What if we need more people to staff the plant? Fuel costs. This is particularly relevant for fossil fuel-based generation, where actually sometimes the fuel cost just goes up. Sometimes you thought that natural gas was going to cost $3 and now it costs $6 and you're in a bad place. And then the discount rate captures the effect of financing and the time value of money. And you have the capacity factor, which reflects the variability in plant utilization due to operational or environmental factors. And so the main method you do this is through scenario analysis, where you evaluate LCOE under optimistic baseline pessimistic scenarios. A wind farm, this is an example of an LCOE analysis, sorry. A wind farm project is evaluated for LCOE sensitivity to capital costs, capacity factor, and discount rate. You have it. So the reason why this example is a wind farm is because this was not done in a lot of places. I was hanging out with my best friend, Sarah Morell, really a lovely woman, and her fiance is a engineer at a natural gas plant. Really such a great guy. And we got to talking about offshore wind, and he was like, yeah, there was this many megawatts of wind promised in New York, and it was this crazy high offshore wind number promised. He's like, only 3 of those are left. And it was like there were 10 originally starting offshore wind projects, and then everyone except 3 pulled out because the capital costs rose and because GE had not put out the turbine that everyone thought was going to be available. And now, because of GE Verona's weird decisions and inability to get the engineering done, and because of the rise in costs, everyone has canceled except some Ørsted and Eversource projects like Sunrise, and those people are renegotiating. So it's a painful time to be in offshore wind, because I don't think people realize that GE might not deliver the goods. And I'm not calling out GE. I love you, GE. I love you, General Electric. But GE didn't deliver the goods, and also interest rates went up, which a lot of people forgot could happen. So you have baseline assumptions, and then you look at how these assumptions are impacted by changing them. And this is something you should be doing in any economic modeling. You should be thinking about how your assumptions impact the eventual outcome. If capital costs increase to $1,800 per kilowatt hour, LCOE rises to 50 megawatts, from 50 megawatts to 60 megawatts, which is not good, and increases the cost. If costs decrease, LCOE drops to $10 per megawatt hour. And this not only helps you think about what sort of assumption you're making and how exposed you are to certain factors, but this also helps you think about where you need to really be focused on making improvements, what you can help. And so also at a 30% capacity factor, down from 35. If you have a lower capacity factor, maybe the wind blows less. LCOE increases to $58 per megawatt hour. So if you drive the capacity factor down, LCOE will go up and the cost will go up. At 40%, LCOE decreases and it becomes more competitive. And then with a higher discount rate, which is effectively what happened here, you have a higher interest rate, LCOE rises, and then if you have a lower interest rate, LCOE will decrease. So if the Fed continues to lower interest rates, renewables will be doing well. If it doesn't, renewables will be having trouble. I'm going to ask you to do a sensitivity analysis on your next homework. So get ready for that, get excited, and have a great day. See you next time. Thank you.